Right now, there is a point in space where gravity becomes so extreme that not even light can escape. You cannot see it, you cannot touch it, but if you crossed its boundary, the universe as you know it would end. Not dramatically, not with an explosion, just quietly, completely, and forever. That boundary has a name. Scientists call it the event horizon. The event horizon is the point of no return, the invisible edge around a black hole beyond which nothing, not matter, not energy, not a single photon of light can ever climb back out. Cross it, and you have left the observable universe behind. You are somewhere the laws of physics, as humans currently understand them, begin to break down. So what would actually happen to you? Let's find out. First, you need to understand what a black hole actually is. A black hole is not a hole. It is not empty space. It is the opposite. It is an almost incomprehensible concentration of mass crushed into an unimaginably small point. That point is called a singularity. The gravity around a singularity is so intense that space itself curves inward, like the surface of a funnel pulling everything toward its center. Light tries to travel in a straight line, but the straight line itself bends. Eventually, close enough to the singularity, every straight line in every direction points inward. There is no outward, there is only in. Most black holes form when a massive star, one at least 20 times the mass of your sun, reaches the end of its life. For millions of years, that star burns. Nuclear fusion at its core converts hydrogen into helium, pushing outward with enough force to hold the star's own gravity at bay. But fuel runs out. The outward pressure drops. Gravity wins. In a fraction of a second, the core collapses. The outer layers rebound in a catastrophic explosion called a supernova. And what remains at the center, if the original star was massive enough, is a singularity, a black hole. Astronomers have confirmed this process across the universe. In 2019, the Event Horizon Telescope, a global network of synchronized radio observatories spanning continents, produced the first direct image of a black hole's shadow. The target was a supermassive black hole at the center of a galaxy called M87, located about 55 million light-years from your planet. The image showed exactly what the mathematics predicted, a dark central region ringed by a bright halo of superheated gas. The event horizon was visible, not metaphorically, literally visible, the boundary between the universe and nothing. Now imagine you are falling toward one. Not M87, that one is incomprehensibly large, with a mass 6.5 billion times that of your sun. Let's use something more intimate. Cygnus X1, a stellar mass black hole about 7,200 light-years from Earth, roughly 21 times the mass of your sun. First identified in 1964 as an extraordinarily powerful X-ray source, Cygnus X1 was one of the first objects ever seriously proposed as a real black hole. The physicist Stephen Hawking famously bet the astronomer Kip Thorne in 1974 that it was not a black hole, and conceded the bet in 1990 when the evidence became undeniable. It is as real as anything in the sky. You are approaching it. You are falling feet first. From a safe distance, nothing seems unusual. The black hole is invisible, black against black. The only sign of it is the behavior of nearby matter, a disk of gas and dust spiraling inward, heating up as it falls, glowing in X-rays. This is called an accretion disk. As you fall closer, you begin to notice something strange. The stars behind the black hole are not behind it. They appear distorted, smeared around the edges of the dark region, bent by the same gravitational lensing that bent that first image from M87. The universe behind the black hole is visible to you, wrapped around it, like a funhouse mirror made of space-time itself. You are now close enough that gravity is measurably different between your head and your feet. The gravitational force pulling on the end of you closer to the singularity is stronger than the force pulling on the end farther away. This difference is called a tidal force. On Earth, tidal forces are gentle. They raise the oceans by a meter or two. Near a stellar mass black hole, tidal forces grow extreme fast. Your feet are pulled harder than your torso. Your torso is pulled harder than your head. You are being stretched vertically while simultaneously being compressed from the sides, squeezed inward. Scientists have a name for this process. It is called spaghettification. That is not a joke. It is the actual technical term used in astrophysics, and it describes exactly what it sounds like. You are being stretched into a thin strand of matter like pulling taffy, because gravity is not uniform across your body anymore. This is the part people get wrong. They imagine black holes as violent and explosive. They are not. They are precise. The black hole does not reach out and grab you. It simply sits there, and you fall toward it, and the geometry of space-time near its center is such that you are gently, steadily, irreversibly unmade. Now here is where things become strange at a deeper level. As you approach the event horizon, time itself begins to behave differently. This is not science fiction. This is a prediction of Einstein's general theory of relativity, confirmed by every experiment ever devised. Gravity bends not just space, but time. The stronger the gravitational field, the slower time passes relative to someone in a weaker field. Near a black hole, this effect becomes enormous. From the perspective of a distant observer watching you fall, say a friend in a ship hovering far away, your image would appear to slow down. You would appear to move more and more slowly. Your image would redden, the light stretched to longer and longer wavelengths by the gravitational field, a phenomenon called gravitational redshift. Eventually, your image would freeze at the event horizon, dimming into darkness, never appearing to cross it. You would look frozen there forever from the outside. You would never appear to fall in. But from your own perspective, something completely different happens. You cross the event horizon and you feel nothing. For a stellar mass black hole, the tidal forces at the event horizon are already extreme enough to be lethal. But for a supermassive black hole, one millions or billions of times the mass of your sun, the event horizon is so far from the central singularity that tidal forces at the boundary are actually mild. You could cross it and feel nothing unusual. No wall, no flash of light, no alarm, just space, and the faint awareness that the universe behind you is still visible, still ordinary, and the awareness that you cannot go back.
Because here is the counterintuitive truth about black holes that most people never hear. A black hole does not pull you, not in the sense people imagine. There is no force reaching out to drag you in. If you fell into a black hole, you would be in free fall. You would be weightless. You would not feel the crushing grip of gravity. You would feel nothing, the same nothing an astronaut feels floating in orbit. What has changed is not the force on your body. What has changed is the shape of space-time around you.
every path forward in time now leads toward the singularity. You are not being pulled. You are simply falling forward through time. And forward through time happens to be inward. The singularity is not a place. It is a moment. It is a moment in your future that you cannot avoid, the same way you cannot avoid tomorrow. Physicists like Roger Penrose, who won the Nobel Prize in Physics in 2020 for his mathematical proof that singularities necessarily form inside black holes, have spent decades wrestling with what actually happens at that moment. The honest answer is, no one knows. The mathematics of general relativity predicts a singularity, a point of infinite density, but infinite density is a sign that the theory itself has broken down. General relativity cannot describe what happens at the center of a black hole. Quantum mechanics, the theory governing the very small, must also apply. But the two theories are not compatible at that scale. A complete theory of quantum gravity would be required to answer what happens at the singularity, and that theory does not yet exist. What does exist is Stephen Hawking's 1974 prediction that black holes are not completely black. Quantum effects near the event horizon cause black holes to slowly radiate energy, a phenomenon now called Hawking radiation. The smaller the black hole, the faster it radiates. Over timescales that dwarf the current age of the universe, a black hole loses mass, shrinks, and eventually evaporates entirely. What happens to everything that ever fell in, including you, is still one of the deepest unsolved problems in theoretical physics. It is called the black hole information paradox, and it has not been resolved. But here is what that means for you, standing on your planet tonight, looking up. Every atom in your body was forged inside a star. You are already the product of a stellar death. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it was produced inside a star that eventually ran out of fuel, collapsed, and exploded, scattering its contents across space. You are the recycled interior of a dead sun. The universe has already passed through you once. You did not notice. And somewhere out there, at the center of your own galaxy, the Milky Way, sits a supermassive black hole called Sagittarius A star. Its mass is approximately 4 million times the mass of your sun. In 2022, the Event Horizon Collaboration Team released its first image of it, a ring of light 27,000 light-years away surrounding a shadow where the event horizon sits. It has been there since before your planet formed. It will still be there when the sun expands and swallows the inner planets billions of years from now. It is not going anywhere. It is simply there, patient, curved into the geometry of space-time, waiting for anything to cross its boundary. Right now, there is a point in space where gravity becomes so extreme that not even light can escape. You cannot see it, you cannot touch it. But every atom in your body has already crossed a boundary once, the moment it left a dying star and became part of the universe again. You are already a survivor of one collapse. You just never felt it.